Hello and welcome to Bay College's Intermediate Algebra online lectures. Today we're going to look at section 9.4, which deals with the ellipse and the hyperbola. The first thing we're going to look at is the ellipse. Now what I have here, an ellipse is similar to a circle, except it's not perfectly round. It's stretched either in the x or in the y, or compressed in the y or compressed in the x. It's not nice and round, okay? It's a circle that's been stretched out. One thing about that is this is the general equation of an ellipse if it's centered at the origin. There's no h and k values. H and k in this case would be 0, just like in a circle. But we notice that we have this a squared in the denominator for our x term and our b squared in the denominator of our y term. Essentially what this means is x has a different coefficient than y. That's what causes our stretch or compression in y or x. So this is standard form of a circle. Now what we have to do is we have to define a few things about an ellipse. Any point on an ellipse is the sum of the distances from these points here to any point on the circle. It's the sum of the distances. That's why we have this addition in here. Now interesting enough is these have a special word. They're called the focus. This is a focus and this is a focus. Together, multiple, we call them foci. So there are two foci in this ellipse. And the sum of their differences, or the sum of their distances, is always a constant no matter where we are on this ellipse. So this is our equation. So one thing we could do is if this is on a graph, and for this particular parabola, or excuse me, ellipse, we're saying that it's centered at the origin. H and k are 0. So what we have to do is we can use something to find the x-intercepts and y-intercepts to have some points of reference from this center here to any other value on this ellipse. Essentially, to find the x-intercepts, this is our tool right here, the a value in the denominator. We have to think, what is a? Well, a is plus or minus the square root of whatever number is down here. Because it's squared, we want to undo it by taking its square root. So we have a negative a and a positive a. Its x-intercepts are going to be some distance to the right, that's our positive a, some distance to the left, our negative a. So the y value for any x-intercept is 0. So we can find the x-intercepts. This point here would be a0. This point here would be negative a0. And the reason why it's plus or minus, well, if I square negative a, I get a squared. If I square positive a, I get a squared. So we have to remember that plus or minus value. If we want to find the y-intercepts, this value here and this value here, well, we can do that simply by understanding what an intercept is. Well, the y-intercept is when x is 0. We're on the y-axis. Well, that's going to give us plus or minus b, because negative b squared is b, or excuse me, negative b quantity squared is b squared, and positive b squared is b squared. Kind of a redundant statement. So this point here is my 0 or positive b, and this value down here is my 0 negative b. So now we're going to tie all this together and actually graph or sketch the graph. If we want to move the camera over here, we'll find our a and b values. Well, if we look at this, I say, wait a second, I don't see a b value. Well, we have to think about it in terms of a fraction. All right? If it's just a value, we can always write it over 1 to have some value there. The first thing we want to do is determine what are these a and b values. What value squared would give me 9? Well, I know it's plus or minus 3. What value squared would give me 1? Well, plus or minus 1, 1 times 1, right, is going to give me 1. Now notice, in order to graph an ellipse, it has to be set equal to 1. That wasn't the case in a circle. So here, we want this to be 1. If it's not 1, we'll see in the next example, we have to do something extra to make it 1. So now with these values, essentially, I'm going to plot 4 points. I'm going to plot my x-intercepts for this ellipse, which are going to be plus and minus 3 when y is 0. So I have plus 3 and minus 3 in the x direction. And then I'm going to plot my y-intercepts, plus 1, minus 1. And notice this one is centered at the origin because there is no h value, there is no k value. So now I can go ahead and graph my ellipse. Pretty simple. If it's in standard form, we can go ahead and we could just find these a's and b's and use those to go from the center, a values to the right, a values to the left. From the center of my ellipse, b value up, b value down. All right, let's look at the next example here. If we look at this one, we notice, hey, this is not set equal to 1. It is not in standard form. So our first step is to say, let's set this equal to 1. That's easy enough to do by dividing all the terms by this constant out here. And then we'll do a little bit of simplifying. So I'm going to write it right here. This here doesn't simplify. It's x squared over 16. But 4 over 16 reduces to a quarter. So I have y squared over 4 equals 16 divided by 16 is 1. Now it's set equal to 1. Again, I assess this and say, OK, I'm not adding or subtracting anything to my x's or y's, so it's centered at the origin. Let's find that a value. A is plus or minus 4. The square root of this is plus or minus 4. My b value, if this is b squared, then b must be plus or minus 2. And now I can go ahead and graph these. Centered from the origin, I'm going to go 4 to the right. I'm going to go 4 to the left. I'm going to go up 2, my b value, and down 2. And now I can graph my ellipse. Pretty simple. All right, let's look at one more example here. We have this ellipse here. We notice it's addition. We have x minus 3 quantity squared over 9, y plus 3 quantity squared over 16 equals 1. Well, it's set equal to 1, but this is different than the other ones. There is an h value in here, something we're adding or subtracting from x before we square it. And there's a k value here, something we're adding or subtracting from y before we square it. So let's do a couple of things. First thing I want to do is assess this is essentially our ellipse, right? Some x values squared over a squared, y value squared over b squared equal to 1. So I want to determine what is that hk value. This is the center of my ellipse. So I look at this and say it's always the opposite of what's in there. So I'm going to write a positive 3. Here, a negative 3. So this is not centered at the origin. It's elsewhere. So I found my hk value. So I'm going to go over to the graph here. And I'm going to plot the center. So I'm going to go 3 to the right for x and down 3 in my y direction. This is the center of my ellipse. Very important concept. Now, looking at this equation, I can determine what a is and what b is. Well, since a is 9, or a squared is 9, I know that a is plus or minus 3. Those two values will give me 9 when I square it. My b value here is 16. So I know plus or minus 4 squared will give me 16. Now, how this is different from the examples we looked at that were centered at the origin, now we're not finding x-intercepts or y-intercepts anymore. We're finding some point on our graph relative to the center. So what I'm going to do is from the center, I'm going to go a units left and right. Positive 3 to the right, so I'm going to go 1, 2, 3. Negative 3 units to the left, 1, 2, 3, and there we are. So I have those two values. Now for my b, I have to go up 4 and down 4 from the center, my reference point. So I'm going to go up 1, 2, 3, 4, and I'm going to go down 1, 2, 3, 4, and now I can draw my ellipse. And you can kind of see this is similar to a circle, but it's stretched a little bit in y. And if we go back to this, well, why is it stretched more in the y? Our b value is larger than our a value, so it's pulling it further in the y. So we have our ellipse there. The next thing we're going to look at is a hyperbola. Now, if we look at the equation of a hyperbola, we see it's very similar to that of an ellipse. there is only one significant difference, and this is one way we can differentiate between what is an ellipse and what is a hyperbola. The sign in between the terms is subtraction. So we're not adding, we're finding the difference between their foci instead of the sum between their foci. So if we look at this, we still see our a squared and our b squareds, but the difference is subtraction. Well, we can have two versions of this because it does matter. We don't want to make a sign error. What if we had y squared over b squared minus the x squared term over the a squared? So we have subtraction there. This tells us something significant about the hyperbola. It tells us the direction in which this hyperbola opens. If we look at this value, if the x squared term is first, it means it opens in the x direction. So we can see here it opens to the left in x and it opens to the right in x. If we have the y squared term first, our positive value, that tells me it opens in the y direction. It opens either up or it opens down. So when you first see this ellipse, recognize that subtraction and you say, okay, now I'm dealing with an ellipse. What direction does it open? Which of these values is the positive value? Which one has the positive coefficient? In this case, it's the x, so it opens in the x directions. This one is the y, it opens in the y directions. Now, we still have to find these values a and b in order to graph this, but we have to use them a little bit differently. The points we're going to graph are going to be plus or minus a and plus or minus b. This actually gives us 4 points. We have positive a, positive b. We have negative a, positive b. We have positive a, negative b. And we have negative a, negative b. 4 points that we can graph. And I'm just going to look at this one right here. This is the 4 points we can graph. And in order to graph a hyperbola, we have to put these 4 points on our graph, and we have to do a little bit with them. So this is my value AB. This is my value negative AB. This is my value negative A, negative B. And this is my value negative A, positive B. So what we do, once we plot these 4 points from our A's and B's that we can determine, we can draw a little rectangle that gives us some idea, some reference point for the center of our hyperbola. In these cases and in the Hawk's learning system, you'll see that the center is going to be 0, 0 for your hyperbolas. It gets a little more complicated when it's not because we've got to move these points all over. So for simplicity's sake, your h and k will always be 0 for this course. Now, once we draw that rectangle, we can draw diagonals through the corners of our rectangle, through our points. What this tells us is the end behavior of the graph. As x gets really big as we go to the right or left, our graph is going to approach these lines. It's going to get closer and closer as x goes to infinity. And since we know that this example, it opens left or right in the x directions, I can start right at the edge of my box in between the 2 points, and I can draw my parabola type shape towards these lines. And these lines are defined as asymptotes. It tells us the end behavior of the graph. What does it look like as it goes further and further? Well, it starts to look like this line. So as we get further away. Same thing with this. The only difference is it opens up or down. So we plot our A and B points. We draw a rectangle so that we can connect the corners with a diagonal dashed line, our asymptotes. And then we could say, okay, well, this one opens up and down. So I start at the center of this little box here, and I go up towards that asymptote, up towards this asymptote, start right here at the center, and move left and right towards our asymptotes. So let's look at an example. Here we have x squared over 9 minus y squared equals 1. I see that subtraction. I know immediately we're dealing with a hyperbola. And because the x squared term is the positive value, it's first here, it opens left and right in the x directions. So I'm going to determine what my a and b values are. Well, a is the value squared that gives me 9. That's plus or minus 3. We look at this and say, wait a second, there's no denominator. Well, we can think of it as being over 1, and it's set equal to 1. That's good news. So I say, okay, plus or minus 1 will give me this value if I square it. All right, so now we're ready to start drawing our rectangle. So I'm going to go plus 3 and up 1. That is the value 3, 1. It's in the first quadrant. Both values are positive. And then I can go negative 3, positive 1. And I can go negative 3, negative 1. And I can go positive 3, negative 1. So now I have these 4 points that I can make a little dotted rectangle. There's my rectangle. Now I have to draw my asymptotes through the diagonals. So I'm just going to go right through here. And I apologize for that not being perfect, but it is what it is. And then I can draw my diagonal this way. And I know that this parabola opens left or right. That x term is first, so I'm going to start right here in the middle of the box and approach those asymptotes. And I make this line nice and dark so we can distinguish it from all the other stuff I had to put on the graph in order to graph it. And that is my hyperbola. Hyperbola. It's more than one parabola, right? One going this way and one going that way. And if we think about ellipses, they are similar to circles. They are similar to parabolas when we look at hyperbolas. And the reason why this is because all of these things, parabolas, circles, and hyperbolas, they're essentially conic sections. They're how we would slice a series of cones. And if we think about what an ellipse is, well, if we have an x squared term, usually that's a parabola. And if we have a y squared term, well, that's just another parabola. What would happen if we added those two together? Well, if I have a parabola and a parabola, I add them together, I end up with an ellipse. What would happen if I subtracted two parabolas? Well, if I subtract them, they're going to go in opposite directions, which is the shape of my hyperbola. So you can think of it that way as well, because we're dealing with these squared terms. All right, let's look at this example here. This is a hyperbola. I know this because I see the subtraction of these squared terms, but it's not in standard form. We have to get it set equal to 1. So in order to do that, I'm going to use this black marker here. In order to get this set equal to 1, I need to divide everything by 36. This needs to be 1. So I'm going to divide by 36 to all the terms, and I'm going to do a little bit of simplifying. So here I get y squared over 9 minus x squared over 36 equals 1. 36 divided by 36. And now I can say, okay, well, it's centered at the origin, as they will always be for this class. Let's determine what our a and b is. Now, this is where we have to be very careful, because this value is not the a squared value. A squared is our x value. So my a is going to be plus or minus 6, the square root of 36. My b value is plus or minus 3, the square root of 9. Now, to graph this, and I should have put my little graph on here before I started, I'm going to plot the 4 points that I can make with the combination of these. I'm going to go positive 6 to the right and 3 up, 3 down. I'm going to go negative 6 to the left, 3 up, and 3 down. Now I'm going to draw my rectangle. Here's my rectangle and my diagonals. And I know this is a little sloppy, but it is what it is. Now, what direction does it open? Let's go back and assess. The y squared value is the positive one. It is first here, so we know it opens in the y, up and down. So I'm going to start right at the center of my box in between these 2 points, and I'm going to approach these asymptotes. Very stretched out here. Notice that's a very large coefficient, so it's stretching it out in the x directions. So it's not getting very big in the y right away. And that is our hyperbola. All right, so let's do a little assessment of what we've covered so far in sections 9.1, 9.2, 9.3, and 9.4. What we're going to look at here is our equations. What have we seen so far? Well, when it comes to parabolas, we can have 2 types of parabolas. We can have a parabola as a quadratic. This is a parabola that either opens up or down, depending on what A is. And we could write this in another form. If we complete the square, we're going to get that value right there. Well, there's actually another parabola that we discovered in 9.2, which was, what if the y value is the squared value? Okay, so this would be a parabola that opens either to the left or to the right, because this is a parabola on its side. It's the y value that's being squared. And we could do the same thing to that, except it'd be x and y. They're inverses. All right, if we look at circles, well, we know that there are two versions of the circle. We've seen that we can have x minus h quantity squared plus y minus k quantity squared equals r squared. This is our circle in standard form. It can also be in general form, where we'd have to complete the square for the x terms, complete the square for the y terms, and write it back into this form for graphing purposes. So we have our standard form and our general form, which is just expanded. We have to unexpand it to get it back to that. We've seen with the ellipse, x squared over a squared plus y squared over b squared. Actually, what we should do is realize that not all of our ellipses are going to be centered at the origin. But we do want them set equal to 1. This is our standard form for an ellipse. And if it's not equal to 1, we divide everything by this constant to get it into this form, reduce any fractions. The hyperbola is essentially the same as an ellipse. The only difference is it's subtraction. We're subtracting these two squared values. This one would open up in the x direction, either left or right. And this one here, make sure I get my right values in there. This one here would either open up or down. So we can see that our two versions of hyperbola in standard form, but notice they're always set equal to 1. If they're not equal to 1, make sure you divide through by that constant to put it into standard form. Now, one thing about this class is you're going to be asked on tests and the final exam to be able to identify the shape of an equation by its form here. So if you see something in any of these forms, you've got to say, hey, I recognize that as a parabola. I recognize either of these as a circle. I recognize this as an ellipse, or I recognize one of these as a hyperbola. One opens in the x directions, one opens in the y directions. So this has been section 9.4, Ellipses and Hyperbolas. Thank you for watching.